Efficiency next, yeah. Oh, and then we have maths after this.
Don't you have 2 hours?
No, 1 hour now and 2 hours next.
Oh.
So 3 hours.
2 hours now.
2 hours now and 1 hour next. Ah. I suppose it doesn't really matter since it's 3 hours me. Right, where are we now? Mechanics and
How much do we have left?
1, 2, 3, 4, 5. Mechanics is the biggest. Yeah. Okay. Power and efficiency.
Nothing happened about our tutorial lesson before the exam?
I didn't see Connell. He's a busy man. I'm a busy man. I'm sure he wouldn't mind if I changed the day. We'll see. Okay, power and efficiency. Where's another? Bank?
We don't know.
Oh. Ma'am. Continue. You have this? Yes? Okay. Stefan? What?
The name.
Yes? In Irish?
Yeah.
Yes, who taught you this? Oh, very good.
She wrote it down just to tell you.
Alright. Okay, so imagine you carried 1 kilogram up a hill. Now imagine 1,000 ants each carried 1 gram up the hill, one by one. So on the top of the hill there are 2 piles. Your 1 kilogram and the ants' 1 kilogram. Who did more work, you or the ants?
Same work.
Same work.
But I did more work than 1 ant.
Yeah, I just mean all the ants together. So if you think about it like this, if you take 1 kilogram up, the work you did is mgh. But if the ants did it 1 by 1, it's still the same, mgh. But what is different between the 2 stories?
Time.
Yeah, long time here, so the time is different here. So although the work is the same, the time is different. This gives us a new idea called power, where power is the work, but how quickly the work is done. So power is the rate of change of work per time. In other words, power is the work divided by the time. How quickly you can do the work. What's the units for power? Yeah, but looking at this, what would it be? Joules per second. So the units are joules per second, which we call a watt. So 1 watt is 1 joule per 1 second.
Power is not units in mechanics, something it's in electricity.
It's easier too.
Yeah. That's why it's not.
Did you write this down?
The unit of...
You can say joules per second or watts.
Yeah, but I mean, preschool and power is same thing. Right?
Unfortunately, yes. So don't mix them up. You got that? Yes? Yeah? You got this?
Yeah.
Yeah? Okay. Continue? What's wrong, Lee? Okay. Continue? Okay. Right. When you convert electrical energy into light energy, you have not used any energy. You just changed it from electrical to light. You converted it. But the electrical energy was converted into light, which is what you want, and heat, which you don't want. So this light bulb here is 100 watts. That means it uses 100 joules per second of electrical energy. How much of that electrical energy do you think becomes light energy? Give me a number. So you're saying 80 joules per second becomes
light
and
no,
20.
actually, it's less than 80. It's less than 50 because it's pretty hot.
Yeah, so what are you going to go with then?
Maybe 40. No, less. It's very little.
You're going with what? How many joules of light do you get per second?
30.
You're going 30, 25, anyone else?
10.
10?
One.
1, yeah.
No.
It's 1. It's 1, yeah. So for every 100 joules that goes into that light bulb, 1 comes out as light and 99 comes out as heat.
So it's
Really?
not efficient as well.
Not at all. Not at all.
Not even the LED lights.
Well, the LED lights are different, yeah. The LED lights would be the opposite.
Yeah.
Yeah.
I was thinking about LED.
Yeah, not these lights though. The old lights.
What's
Yeah.
an LED light? Could you give me an
LED, it will be.
Screen.
Wait, what is an LED light?
No, can you give me an example?
The numbers.
I know that there are some LED screens.
Yeah. So, like, you can get LED light bulbs. They look like normal light bulbs.
Are they the yellow ones?
No.
They could be yellow. That would be the cheap ones, maybe. But you can get LED light bulbs that look like normal light bulbs.
Your phone screen.
Yeah.
Phone screen would be
LED.
type of LED. Probably not LED anymore. It's probably something else.
What's the difference?
Yeah, it's like the opposite. So 100 joules would make 99 light and 1.
Yeah, but what makes it so efficient, that LED ones?
The LED, it's the material that's used. So this uses a material that gets really hot when a current passes through it. Whereas LEDs use, LEDs use, I don't know, semiconductor materials.
Silicons.
They're more expensive though to buy.
But they last longer. And
Yeah, but I have these bulbs at home and I don't feel like they last that longer. Because the bulb says on it you replace it every, 10 years. I'm like, well, how come I've replaced it 3 times? And I've only lived in the house 9 years, you know? So, they're supposed to last longer, but I don't know if I believe that. Okay? Alright. So next, it turns out it's actually only 1. So this gives us the idea of you said efficiency. So efficiency is a percentage. Is efficiency good or bad?
the higher the efficiency,
Yeah,
the better.
it's good. So it's the energy that's useful as a percentage of what you put in. So in other words, it's useful output over total input times 100. So for my old light bulb, what was the efficiency?
1%.
1%. And my new LED light bulb is 99%. Yeah.
So
Is fire more efficient than those
no.
bulbs? If it's 1%?
No, it still would be, but it's not much different, I know. What's your question?
So it depends on like what we're using it for.
Oh yeah,
So like they would be more efficient for heat than.
you're right, it depends on your point of view. This is why we use the word useful. Now, there is you can state the formula slightly differently. So, and of course, you would like efficiency to be 100%, but because of heat loss, It can never be 100%. Also, if we divide by T, what's work divided by time?
Power.
And work divided by time?
Power.
Power. So you could rewrite the formula as useful power out over total power in. It's the same result. It depends what you know, but it's the same result. It might be worth noting that. You got that? Yeah? Yes? Okay, so just before I go on to that, just for context, what would you say the efficiency of a car is? Just a regular car.
Efficiency of what?
The engine. So the work that goes in, or the energy that goes in, comes from the petrol, and the work that's done is moving the car from, the kinetic energy. So what would you say the efficiency is here? Because you know energy is lost, the car engine gets hot, so this is wasted energy. So what would you say the efficiency is for a car?
The car have a turbo?
10?
No, let's say it is a a 1.2 litre Honda Accord.
10 to 20%. Or even less.
I think if it's just something like a Honda, maybe 20 to 25, if it's a new car. If it's something like an American car, a Ford or something, it's probably more like 10 to 15. And if it's a SUV, forget about it, it's like 5%. I mean, you know those, what do you call those, the Hummers, is it the big American Hummers, isn't that what they're called?
Yeah.
Arnold Schwarzenegger has one. These are terrible, they're like 1% or something, you know, because they're so big, it's such a waste of energy to move them around.
It depends on
How much petrol it uses.
Yeah.
And how far you can get out of it.
Yeah.
Fuel coverage.
It's really low.
8 cylinders and 12 cylinders.
That affects the efficiency too.
But then it depends on the weight.
And that too. So like something like a Nissan Micra or a Toyota Yaris, they would be pretty high. A saloon, like a Honda Civic or a Honda Accord, they'd be a bit lower. And then SUVs, they would be the lowest.
But then they'd be faster.
Yeah, and this is the balance, you know. The small cars won't have as fast a top speed.
But then they'd cover like the same distance over a shorter period of time.
True, but all you care about is how much petrol you use to cover that distance, and you would need less petrol in a smaller car, so it's more efficient. Okay, let's have a look at some questions here. So, here's a simple one for you to practice. A boy lifts a 2 kilogram book off the ground, a height of 1.1. It takes him 2 seconds. So firstly, what is the power? Well, what's the formula for power? Work over time. And what work is he doing?
Lifting the book.
Yeah, so what type of energy is that?
Kinetic. The potential.
Potential. He's given the book potential energy. Okay. See what you get, and then I'll open up the calculator here. Power.
Yeah, 10
Let's have a look then. So the work is mgh. You got that? mgh. So what's the m? 2, the g 9.81, and the h 1.1. So yes, question?
Oh, no.
Oops, sorry. No, what are you saying?
No.
You take back your question?
Yeah.
Okay, alright. So let me just open up the calculator. Work is mgh and the time is 2. So work mgh H, and the time 2. So the final answer is 10.8 watts is the power. Okay. Now, he got this energy from his breakfast. However, half the energy is wasted as heat. What is his power now? Okay, so I tell you, the efficiency is 50%. So that means power out over power in times 100% equals 50%. So power out over power in equals a half when you divide 50 by 100. Power out, we know. What is the output here? What is he doing? He's lifting the book. This is the output. So this is still mgh. The power in, what's the power in here?
Half mg.
No, what is it? No, what is it?
The food that he ate. The energy provided by the
The
food.
heat
that-
and
The chemical.
Yeah, in other words, from his muscles, So his body is the engine. This is the power going in. The output is lifting the book. There's energy lost between him, the engine, and the book being raised. Where would this energy be lost? Heat, sound. Right, so that's a half. So power in is mgh over, no, sorry, I got that backwards, isn't it? 2 mgh, isn't it? 2 mgh. So in other words, it's twice the previous answer. The previous answer was that. So the new answer is 21.6.
Okay, so if someone was at the gym and they were lifting weights and they don't yell, does that mean they can carry more weight?
No, the gym is different.
Yeah, it's
when you
different.
train, you're stronger.
No,
Yeah.
it's kind of because you
It's
want to-
psychological.
Yeah,
Yeah.
psychological. But then it does, if you don't, does that?
No, it just means you're burning more calories by making the sound. Not that it makes you more or less powerful. So in other words, your protein bar will be digested quicker. Yeah. Okay. Continue. Right. Okay. Try this one now by yourself, and then I'll do it. So in part A, it's 100% efficient. Part B is 40%. Now 40% would be a pretty good rating of a car. It might be like a hybrid or something like this. So see what you can get for this one now, please. Got an answer? Yeah? Okay, so right. So firstly, what's the work done? The work done is to give the car kinetic energy, which is a half mv squared. What was the m?
1,200.
And the v, did you convert
100
it?
kilometers per hour. 27.78.
100 kilometers per hour, you say, which is 250 over 9, which is the 27.78 squared. So if I just square this, times it by 600, I suppose. This is the final answer. Yeah?
Yep.
463 kilojoules. Yeah?
Yeah, that's fine.
Okay. And then part B is if it's 40% efficient. So, will the engine need more power or less power? Or, sorry, will it do more work or less work if it's 40% efficient? No, the engine will do more work because not only does it still have to produce this kinetic energy, it's also wasting energy by producing heat. So, by being inefficient, the engine is doing more work.
You wanted the input or the output?
The input, the output doesn't change. It's still the same useful output.
Kinetic energy,
Doesn't change.
efficiency.
By changing the efficiency from 100 to 40, the engine now has to do more work to achieve the same output.
Yes.
Yeah, I know this. Yeah. I don't know if they know this. Are you happy with that or not?
Yeah.
So, I said the efficiency is 40%.
So 1.4.
So power out over power in, or work out over work in, whichever.
I thought it was 50.
Oh wait,
Can we just
I didn't work out the power yet. This is only the work. I asked for the power, didn't I? Yeah, okay. So there's one thing left to do. What's the power? Yeah, work over time. You divide by 10, so that's 46.3 kilo
Joules per kilowatts.
Okay, now part B. The efficiency is 40%, so power out over power, power out over power in times 100 equals 40. So power in would equal 46.3 times 100 over
No, it's 40.
yeah, like this.
Yeah, yes.
Done. Yeah. So, divide this by 10. That was the 46.3 kilowatts times 100 divided by 40. So, it would now be 116 kilowatts.
Why can't we just multiply it by 1.4?
Yep, that's fine.
Yeah.
Yep, that works fine. It's just in the exam they like to see formulas being used, you know. Okay.
Can you go back to the question, please? Okay.
You got this written down? You got this answer? Did you use kilowatts? 10 to the 3? You wrote the full number out?
I'm still not sure of my thesis.
What do you want to study next year? Oh, well, learn them now. You don't want to be in the middle of a lecture hall and put your hand up and go, teacher, the kilo, which one's that? I can never remember this. It's easier for you if you learn them now, okay? Alright, continue. Right. So, these questions are not really that difficult. I know that looks like there's a lot here, but they only take 1 or 2 minutes to do. So I would like you to try and get them finished now, and then we'll start the next lesson. Let me just save these videos.